Okay, good day. For today, we'll have the special functions. So in this section, we're going to discuss two number theoretic functions. These are the tau of n, or the number of positive divisors of a positive integer, and we have the sigma of n, which is the sum of the divisors of that number. So properties of perfect and amicable numbers, special numbers that fascinated mathematicians through the years, will be discussed in this topic. Okay, so let's start first with the sum of divisors of a number. So given that we have a positive integer n, then we shall denote the number of positive divisors n by tau of n, and the sum of the positive divisors of n by sigma of n. Okay, so now let's have an illustration. So let's say we have n be equal to 12. Okay, so let 12 be the number. So then the positive divisors are 1, 2, 3, 4, 6, and 12. And we know that 2, 3, 4, 6, and 12 are the divisors, okay, of the number 12. Okay, in addition, if we have that tau of n, all we need to do is to count, okay, those positive divisor, which are 1, 2, 3, 4, 6, and 12. And that is 6. Okay, so therefore the tau of n here, or the total number of positive divisor, is 6. And also, when it comes to the sigma of n, all we need to do is to add this. Okay, so we have 1 plus 2 plus 3 plus 4 plus 6 plus 12, and we have the sum of the positive divisors of 12, which is 28. Okay, so also, in addition, we're going to have the idea of the prime factorization here. We're going to apply another formula for us to identify the number of positive divisors and the sum of those positive divisors. So in this case, we have 12 is equal to 2 raised to 2 times 3. So that's the canonical form, or the prime factorization of 12. Okay, so notice, given that we have 12 and we have the prime factorization of 2 raised to 2 times 3, we can say that the prime number 2, okay, has three possible choices for the exponent. Namely, it could be 2 raised to 0, 2 raised to 1, 2 raised to 2. So it's either 1, 0, or 2. Okay. In addition, with 3 as a divisor, it may appear as 3 raised to 0 or 3 raised to 1. Right? So it has two possible choices. Okay, so in this case, we have that 3 times 2, that is 6 possible divisors. Okay, so 3 is the number of ways 2 may appear as a divisor, and 2 as the number of ways 3 may appear as a divisor. So in this case, if we have the generalization, okay, of this idea, we can say that given that we have the prime factorization of that number, p sub 1 raised to a sub 1 times p sub 2 raised to a sub 2 times up until p sub k raised to a sub k. Okay, so let's say we have the exponents. Okay, we have the exponents of all those prime numbers, or prime factors. So in this case, we can say that there are a sub 1 plus 1 choices for the exponent of b sub 1. We have a sub 2 plus 1 choices for the exponent of b sub 2, up until a sub k plus 1, which are the number of choices for the exponent of p sub k. Okay, so in general, if we have this idea, we can say that the total number of divisors of n is this. Okay, in symbol, we have the formula. Tau of n is equal to, again, all you need to do is to look at the exponents, okay, of those prime factors. So we have a sub 1 plus 1 times a sub 2 plus 1 times up until a sub k plus 1. Okay, so we're going to utilize this formula for us to identify the tau of n, okay, or the number of positive divisors of the given number. So let's go back to the number 12. Okay, so given that we have the prime factorization of 2 raised to 2 times 3, And as you can see, we have here the exponent for 2 as 2, and then we have for 3 as 1. Right? So we can have this again as 2, and then we have that 1. So in this case, if we're going to apply the formula, we'll have that 2 plus 1 times 1 plus 1. So quantity 2 plus 1, that's 3, times the quantity of 1 plus 1, which is 2. So that's 3 times 2, that is 6. Okay, so therefore, the total number of divisors, or the tau of 12, is 6. Another example, given that we have that 75, and the prime factorization for 75 is 3 times 5 raised to 2. Okay, so again, look at the exponent. So given that we have 1 as the exponent of 3, and then for 5, that is 2. So let's just apply that again, the formula. We'll have that quantity 1 plus 1 times the quantity of 2 plus 1. So therefore, that is 6. Okay, so therefore, there are 6 number of positive divisors for 75. Another one, let's say we have the number as 120. So the prime factorization for 120 is 2 raised to 3 times 3 times 5. So in this case, we have 3 prime factors. So there are 3 exponents here. So namely, for 2, that is 3. And then for 3, that's 1. And then for 5, that is 1. So that is 3 plus 1 times the quantity of 1 plus 1 times the quantity of 1 plus 1. So that is 16. So therefore, there are 12 positive number of divisors for 120. In addition, we have also the idea of the sum. Okay, the sum of the positive divisors of the given number. Okay, so given that prime factorization, we'll have this formula. Okay, so we will get that prime raised to a sub 1, so that's the exponent, plus 1 minus 1 all over, again, the prime number or prime factor, which is p sub 1 minus 1. Then again, for another prime factor, you'll just repeat that. Okay, you add 1 to the exponent, and then with that, minus 1 all over the prime factor, minus 1 again, up until to the last prime factor. Okay, let's have an example. Okay, so let's say we have, again, the 12, and we have the prime factorization as 2 raised to 2 times 3. So again, we have the sum or the number of positive divisor, which is 6. And then for the sigma, or the sum of those positive divisors, we're going to have this. Okay, so we have that 2 raised to 2 plus 1 minus 1 all over the prime factor 2 minus 1 times the quantity of the other prime factor, which is 3 raised to 1 plus 1 minus 1 divided by 3 minus 1. And then if we're going to simplify this, the sum of the positive divisors of 12 is 28. Okay, which is true from our illustration from the previous slides, that the sum of the positive divisors of 12 is 28. Okay? Let's try another one. So let's say we have 75 again. So the prime factorization for 75 is 3 times 5 squared. So that is, again, for the tau, that's 6, the number of positive divisors. And then for the sum of those positive divisors, we'll have this. We have 2 prime factors, so therefore we have this. So we have that 3 raised to 1 plus 1 minus 1 all over 3 minus 1. And then for the other prime factor, which is 5 raised to 2, add 1, and then minus 1, divide it by 5 minus 1. So if we're going to solve that, the sum of the positive divisors of 75 is 124. That is 124. Next one. How about 120? So we have that prime factorization again. And then let's substitute it to the formula. So we'll have, again, the tau, or the number of positive divisors, 16. And then for the sum of those positive divisors, we have this. Since we have 3 prime factors, so we have this 3. Okay, and then if we're going to solve this, the sum of the positive divisors of 120 is 360. Okay, so all you need to do is to just apply this formula, okay, to get the sum of those positive divisors of the given number. Another one, we have the concept of the perfect numbers. Okay, so an integer n is called a perfect number if we have the sum of the sum of those positive divisors of that number is equal to twice of that number. Okay, 2 times of that number. Okay, so let's have an illustration. So let's say we have 6. We have 6 as our number here. So let's say we solve for the uh, sigma, okay, or the sum of the positive divisors of that. Okay, so in this case, we have that 2 raised to 1 plus 1 minus 1 divided by 2 minus 1, and then 3 raised to 1 plus 1 minus 1 divided by 3 minus 1, and that is 12. Okay, that is 12. So in this case, we have 12 for the sum of the positive divisors. So now, let's have the twice of that number. So 2 times 6, that's 12. So as you can see, that's true. So we have here, again, the sum of the positive divisor is 12. Okay, and then twice that number is also 12. It's also 12. So in this case, we can say that 6 is a perfect number. Another example. Let's say we have that 28. Okay, we have 28. So let's say again we have the prime factorization, which is 2 raised to 2 times 7. And then the tau of 28, so that is 6. Okay, so there are 6 positive divisors. So in this case, again, let's just solve for the sigma or the sum of those positive divisors. And then we apply again the prime factorization and its formula. So we have here 2 raised to 2 plus 1 minus 1 divided by 2 minus 1 times the quantity of another prime factor, which is 7 raised to 1 plus 1 minus 1 divided by 7 minus 1. So if we're going to solve that, we'll have that as 56. Okay, we have that as 56. Now, if we're going to identify the twice, okay, of that number, 28, so that's still 56. So we have that sum of positive divisor, which is 56, and then twice of that number is 56 also. So therefore, we can say that 28 is a perfect number. Okay? Euclid's formula for perfect number always lead to an even number. Since 2 raised to p minus 1 is even for p is greater than 1. So we're going to utilize a formula that they identify with the perfect number. Okay, so as of the moment, 23 centuries later, there's no odd perfect number has been found. Okay, it's always even number. That is the perfect number. Okay, so we have this formula. So n is a perfect number if and only if we have that n is equal to 2 raised to p minus 1 times the quantity of 2 raised to p minus 1. Okay, where p and 2 raised to p minus 1 are prime. Okay, those are prime numbers. Okay? Pythagoras found out that the perfect number is the set of a series of consecutive rational numbers. In addition, an even perfect number has a unit digit as either 6 or 8. It's either 6 or 8. From the first two examples, we have that 6 as the perfect number, and the other one is 28. Okay? So take note of this facts about the perfect number. Okay, so let's have another example. Okay, let's apply this formula. Okay? So let's say we have another one which is 496. So the prime factorization of 496 is 2 raised to 4 times 31. Okay, and then if we're going to identify the number of positive divisors, if we're going to apply it again, we have the tau of 496. So again, just apply the formula. We'll have 10. Okay, and then for the sum of those positive divisors, we have that, again, we have two prime factors. So we have this 2 raised to 4 plus 1 minus 1 divided by 2 minus 1. And then the other prime factor, which is 31. So 31 raised to 1 plus 1 minus 1 divided by 31 minus 1, which is 992. Okay, and if we're going to identify the twice of that 496, still 992. Still 992. So in this case, as you can see, we can have its expression based on this. Okay, so let's say we have the 2 raised to 5 minus 1, and we multiply it to 2 raised to 5 minus 1. Okay, so that is 2 raised to 4 times 2 raised to 5 minus 1. So we can express that 496 as this one. Okay, still, again, so given the fact that we have this, and 496 is a perfect number. Okay, 496 is a perfect number. Let's have another example. Okay, so let's say we have that 8,128. So the prime factorization for 8,128 is 2 raised to 6 times 127. So in this case, we have, again, the exponent 6. We have 1 for 127. So we'll have the number of positive divisors, 14. And then for the sigma, okay, let's just apply it. Again, we have two prime factors, 2 and 127. So we'll have this. So 2 raised to 6 plus 1 minus 1 divided by 2 minus 1. And then the other factor, so we have that 127 raised to 1 plus 1 minus 1 divided by 127 minus 1. So that is 16,256. And then 8128 times 2 is 16,256. Okay, so in this case, again, equal. So we can say that this is a perfect number. This is a perfect number. And it can be expressed again with this form, in this form. So we have that 2 raised to 7 minus 1 times the quantity of 2 raised to 7 minus 1. Okay, which is 2 raised to 6 times the quantity of 2 raised to 7 minus 1. Okay, so again, 8128 is a perfect number. Another definition for perfect numbers, a positive integer that is equal to the sum of its divisors except itself. So let's go back to the 4 examples. So let's say we have that 6. And again, we have 4 positive divisors here, which are 1, 2, 3, and 6. So if we're going to add that 1, 2, and 3, it is equal to 6. Okay, that's true, right? Based on its definition and this illustration, this is true. Another 28. So if we're going to apply again the tau of 28, so that's 6. So those are 1, 2, 4, 7, 14, and 28. And then let's add all those positive divisors except 28. And still we have the sum, which is 28. 1 plus 2 plus 4 plus 7 plus 14 is 28. And same goes with 496. So there are 10 positive divisors, namely 1, 2, 4, 8, 16, 31, 62, 124, 248, and 496. And still, if we're going to add all of the positive divisors except for 496, still we'll have that 496. Same goes with 8128. Okay, so we have 14 positive divisors here. Those are 1, 2, 4, 8, 16, 32, 64, 127, 254, 508, 1016, 2032, 4064, and 8128. So if we're going to add that except 8128, the sum of that is 8128. Okay, so the perfect numbers is a perfect integer, a positive integer that equals to the sum of its divisors except itself. Okay, let's have this last one. We have amicable numbers. a pair of numbers whose sum of all the divisors of the numbers, excluding the number itself, is equal to the other. Okay, we call this as amicable numbers. We call this as amicable numbers. So let's have an example. Let's have an illustration. So let's say we have here 220 and 284. So let's identify if 220 and 284 are amicable numbers. Okay, so let's try to identify again the positive divisors of 220. So we can express that in prime factorization or in its canonical form 2 raised to 2 times 5 times 11. And the the positive divisors rather are 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, and 110. Okay, again, except for the number itself. Okay, and then we have 284. So it can be expressed as 2 raised to 2 times 71. The positive divisors except 284 are 1, 2, 4, 71, and 142. Okay, so and then if we're going to add this, okay, if we're going to add this and then we're going to add this also, okay, we'll have for 220, the sum of that is 284. And for 284, the sum of that is 220. So notice, this is considered as amicable numbers. Okay, this pair is considered as amicable numbers. Okay. Okay, so if we're going to apply again the sigma formula, okay, we'll have this, right? If the sigma of A is equal to the sigma of B, okay, and then this is equal to the sum of the two numbers, then we can consider that as amicable numbers. Okay, so in this case, if we're going to apply, again, the sum of the positive divisors, so that's 504 for 220, and then for 284, still that's 504. And then if we're going to add that 220 and 284, we'll have 504. So as you can see, this is still true. Okay, for this definition. So therefore, we can say that the pair is amicable numbers if given that integers a and b, we have the sigma of a is equal to the sigma of b, and it is equal to the sum of a and b. Okay, those are we considered as amicable numbers.